In part 3 of chapter 11, which is data storage, we will look at the following three sections. Section 5, which talks about flash memory, section 6, which talks about memory expansion, and then finally section 7, which talks about special types of memory. So let us first begin the discussion on flash memory. The discussion will focus on the basic characteristics of flash memory, the basic operation of flash memory cells. We will compare flash memory with other types of memory and discuss the USB flash drive and how it's made. So the flash memory itself, it's a high density read-write memory, which means you can read and you can both read and write into this memory. It's non-volatile, which means it doesn't lose its memory even when power has been turned off. And the basic structure is the storage cell, and each storage cell, the storage cell of the flash drive with a floating MOS transistor, which means metal oxide semiconductor transistor, MOS. So data in this storage cell in the MOS transistor is stored as a bit. It's either 0 or 1, which refers to either the presence or the absence of charge. So the presence of charge will represent a 0. The absence of charge will be representing a 1. Now, a typical example of a MOS transistor or symbol is as shown here. So the MOS transistor will have a control gate, the drain, the source, and a floating gate. So the presence or absence of charge within the floating gate is what determines what has been stored in the flash transistor. So in this case, if there is positive charge in the floating gate, there will be a 0 stored. If there is little or depleted or absence of charge in the floating gate, there would be 0 stored. So there are 3 operations typically that can be done on a flash memory. That is programming, reading, and erasing. Programming is the initial process of adding electrons to the flash memory cells, that is the MOS transistors. So this is done by adding a positive voltage on the control gate with respect to the voltage at the source, and this will attract electrons into the floating gate. And of course, if when these electrons are attracted to the floating gate, a 0 will be stored, whilst the MOS transistors or the cells of the flash that need to store a 1 will have no charge, will have a depleted state of charge, so it will be left without the charge. And once the charge has been stored up into the flash drive, it can last for long periods of about 100 years without the need for external power. So it really retains its memory for a long time. So the read operation occurs by applying a positive voltage on the control gate, and the way the flash cell is read is by determining whether or not the transistor will be turned on. So the amount of charge stored in the floating gate will determine whether the transistor is turned on or not. So take for example whereby you have a 0 stored, that is, you have a lot of negative charge within the floating gate. When a positive voltage is applied at the control gate, because of that positive voltage, because of the negative charge inside, the transistor remains off. Therefore, the voltage VDD, which is the reading voltage, is unable to turn on the transistor. In that case, the output of the transistor is read as 0. This will signify that the MOS transistor is stored as 0. Secondly, alternatively, in fact, when a 1 has been stored, when the positive voltage is applied and there is no charge on the floating gate, the transistor will turn on, and so the current from VDD will begin to flow to the drain, And then this, then because the transistor is on, this will be read as a 1. For the final operation of erasure, a charge, so erasure works by removing the charge in the memory cell. And the way it's done is that a voltage is applied on transistor source at this particular end, and this positive voltage will attract the charge that has been stored within the MOS transistor and extract it from the transistor, thus erasing the contents of the transistor. So an erased flash memory drive will not have any charge in any of these MOS transistor cells. So this figure shows a typical memory array of a flash memory, and access is granted one row at a time. So for instance, each of these cells will store a different bit. Now if row A, let's say row 0 is been selected, what happens is the only cells in row A would be read out. So, and the output will be read out at the comparator. So if row 0 is read, there will be data at comparator number 0, number 2, number 3, and so on up to comparator number M. The comparator output is simply a comparison of the voltage difference between the voltage on the bit line, this is the bit line, compared to the reference voltage, which is given within the flash drive itself. For example, if a 1 is stored, which means there is no charge on the floating gate, and a positive voltage is placed on row select here, number 0, what happens is that the MOS transistor will turn on, which means there will be current flowing along the bit line. Because of that current, there would be a voltage drop that is sensed out by the comparator, and this will be read out through the comparator to read out a 1. If on the other hand a 0 has been stored, which means the floating gate is full of charge, it means the transistor will not be turned on. Therefore, no current will be flowing on the bit line, and so there won't be a voltage difference out of the comparator. In that way, the memory array will put out a 0, a binary 0. Now this shows an example of different packaging of the flash drives. You have a normal USB flash drive or common USB flash drive. You could have it in the form of an SD card or a smaller version of the SD card, which normally goes into the phones. So a typical USB flash drive is made up of multiple subcomponents. Apart from the memory array, which is the flash memory that we've just been discussing, it would have a USB connector. The USB connector has 4 connection points or 4 lines. That would be the positive voltage, the negative voltage, which are on both ends, and then in between it has 2 data lines where the data has been transferred. That is the positive data line and the negative data line. And the connector connects directly to the mass memory controller, through which it can be used to read the flash memory. And all of this, the mass controller operation is guided by a clock input, which is provided by the crystal oscillator. We can compare then the property of flash memory to other types of memories, which we have already covered in earlier sections of the chapter. We see that flash memory, for instance, is non-volatile, much like the ROM and the EEROM, and unlike the RAM, which loses its memory when there is no power. We can also see that flash memory is high density, much like the ROM and the dynamic RAM version, and it uses a single transistor per cell, memory cell, like the dynamic RAM, but not like the static RAM. And then with flash drive, remember you can both read and write, so you can write it in system writability is yes, like all of the RAMs, but not like the ROMs, except for EROM, which has a special characteristic in this case. In the subsequent section of the lecture, we will consider memory expansion, which is section 6 of the prescribed text. We will define word length and show how to expand the word length of a memory, and then define word capacity and show how to expand word capacity of a memory, and then finally discuss the different types of memory modules. Word length expansion simply refers to increasing the number of bits in data coming out or going into a memory. For example, in the example below, we will consider increasing, expanding, doing a word length expansion from 4 to 8 bits by, that is moving from a 65,506 by 4 ROMs, taking 2 of those and then connecting them together to give you a 65,536 by 8 ROM. The way, of course, we normally refer to this ROM is taking a 64K ROM, a single 64K by 4 ROM, or in fact 2 64K by 4 ROMs, and then converting them to a single 64K by 8 ROM. So in this case, we have these two separate 64K ROMs, which have the address bar and the control bus, and they each store 4 bits, and then they can each retrieve 4 bits of data onto the bus. So we need to expand the word length to 8 bits. And the way we do it is to arrange these 64 bits from this way. We have ROM 1, ROM 2, and then the address bit, the 16-bit address, will go to both ROMs simultaneously, as well as the control bus will go to both of them. And then we will have then at the output, since these ROMs would be addressed by the single address bus simultaneously, the output data that comes out will have to be 8 bits now. So it's as simple as that. So here's an example. Consider the following 64K by 4 ROM, which means the addresses here, there's 16 of them from A0 to 15, and then the output is 4 bits, bit number 0 to 3, and then you have this control bus here, which is composed of the enables. If we want to expand this to from a 4-bit word length to a 16-bit word length, the question is how many units would we require of these 64K ROMs? The answer to that question is simply 4, and the way in which you are going to configure the system of the newly expanded word length memory is that the 16-bit address will address all of the 4 ROMs simultaneously, and then the ROM 1, ROM 2, ROM 3, ROM 4 will each put out their data onto the data bus, with ROM 4 being the most significant bits, and then the next most significant bits coming from ROM 3 all the way up to the least significant one, which is ROM 1. And the control bus will be connected together to enable the memory to function. So all of that will be connected to the same enable link. So far we have considered word length expansion for ROM only. However, this can also be done for RAM memory. But what we need to be mindful of is that in the case of the RAM, data can be both read out and be written into the memory, whereas the ROM, it was just about reading the data that comes out of the memory. So in this case, the setup is similar, the address bus is combined to address both of these memory modules. In this case, if we wanted to expand our word length from n bits to 2 n bits, we will combine these two RAMs, RAM1 and RAM2, and then we will then combine the control bus as well. However, the data bus will be bidirectional, in the sense that data can be read both into the memory as well as out of the memory. Word capacity expansion, on the other hand, refers to increasing the number of addresses in a memory system. For example, we could move from storing 1 megabits to 2 megabits. The example shown below shows an example whereby we are doing a word capacity expansion from 1 million, from about 1 million addresses, whereby we have 20 bits addressing a single RAM, to having twice as that, 2 million addresses. And the way this can be done is simply by in the following configuration. So we add a single bit, the most significant bit of an address, just one, so that we enable one of these RAMs, one of the memories at once. So in this case, we just add a single bit, the 21st bit of the address bar, and then this 21st bit will go to the enable input. It will be connected so that not both of them are on at the same time. So when bit number 21 is low, only RAM1 will be enabled, and when bit number 21 is high, RAM2 will be enabled. And then this will result in the whole memory system having twice as many addresses to store the information. The following is a word capacity expansion example. So we have, in this case, a single unit of RAM, which is a 512K by 4 RAM, and we want to do a word capacity expansion from 512K to 1 mega. Now, remember, what capacity is all about increasing the number of addresses in the memory. So how do we then achieve the 1 meg capacity? We can see that, in fact, for the current RAM, which is 512K, there are 19 address lines, which means 2 to the power 19 is actually gives us the 512K. And if we want to move to 1 mega, we will need to have 20 of these address lines. The answer to this question is simply by adding the second module of RAM. And the way you do it is that you attach all the address numbers 0 to 80, you attach them to both RAM number 1 and RAM number 2. So this would go, A0 would go to both RAM number 1 as well as RAM number 2. A1 would go to both RAM number 1, RAM number 2, A2, A3, A4, all up to A18 would go to RAM number 1 and RAM number 2. And that will be done with the address lines, because you only have 19 address lines in each of these RAMs. Now, you need to expand this by putting in an extra address line, which is A19, the 20th one. And the 20th one would go to the enable. That is, it will now reduce the number of lines in the control bus. And then the first one will go to enable enable E0, and the inverse of that will go to enable E0 on RAM number 2. This simply ensures that not both of these RAMs are active at the same time. So when one is active, the other is inactive. In that way, you can address all of the memory locations in RAM number 1, and then ultimately address all of the memory locations in RAM number 2 when A19 is 1. When A19 is 0, you'll be addressing RAM number 1. When A19 is 1, you'll be addressing RAM number 2. And your control bus remains the enable input to E1 on both of the RAMs. In that way, you have just doubled your number of addresses, whilst the output data simply has the same 4 bits. The output data bus has 4 bits. Looking at briefly the types of memory modules, you will see that SDRAM memory in particular is available in modules consisting of multiple memory ICs on a breadboard. So this would be the breadboard, a semiconductor breadboard. And they come in 2 variants. There will be the older SIM, which is a single line memory module, or the most common type, which is the DIMM, the dual line memory module. And both of these would fit into a socket on a system board or a motherboard. So DIMM, the most common type of DIMM, is what's called DDR, SDRAM. The DDR meaning double data rate. The reason why it's called double data rate is because 2 blocks of data are accessed for each clock cycle, as opposed to a typical SDRAM whereby only 1 block of data is accessed per clock cycle. So it's double data rate. And there are multiple types of double data rates, and they differ with the number of pins that they have, as well as the source voltage that they use. So there will be DDR 1, 2, and 3 differing based on those 2 specifications. For this section, we'll consider special types of memory. We'll look at FIFO, LIFO, discuss the use of memory stacks, explain how to use a portion of RAM as a memory stack, and then describe the basic CD memory. So first of all, FIFO memory. FIFO simply means first in, first out. It's an arrangement whereby the first bit to get into the memory will be the first one to come out. So the first bit to come into the memory will be the first one to get out, and then they follow each other that way. So it's a special type of memory, and it's made up of an arrangement of shift registers, that is FIFO registers. So this is an example of a memory array that stores 64 4-bit data words. So this would have 64-bit shift registers, 4 of them, in the following arrangement, whereby you put in your data at the input buffer and it comes out at the output buffer. And this data is controlled by the input logic control, the marker register, as well as the output logic control. So at every clock cycle controlled by the marker register, the input shifts into the memory buffer, and then up until it emerges out of the output buffer. And the principle is that the first set of bits that came into the memory buffer are the first to come out. A typical application of a FIFO would be in terms of buffering. Buffering is when you have an intermediate storage of data, and this can be applied when you have, for instance, irregular telemetry data that you are receiving at irregular samples, and you want to transmit it at a constant rate. So you would buffer it, you would collect that data up until it's ready to be transmitted at a constant rate. Another example is when 2 communication systems, so generally speaking, when 2 systems that are communicating to each other have different data rates. For instance, if the keyboard on the computer is much slower than the processor, then what would happen is that the keys that have been typed on the keyboard will be stored into a buffer, and then finally when the buffer is full, they will be processed at a much higher rate, as opposed to the processor having to wait for each and every key as it's processing. Another example is when you have a data input at a constant rate, but you want to put it out as a single output, that is in the form of a burst. So there can be many examples of using FIFO special type of memory. Another special type of memory is a LIFO memory, last in, first out. So data is stored and then recalled in reverse order. So in this example, if when data comes into the memory, the pink block, the purple block comes in first, then the green block, then the yellow block. When it's retrieved, the last block to come in, which is the yellow block, will come out first, then the green block, and then finally the purple block, which was the first to come in. So it's last in, first out. And this structure, where the memory itself is normally referred to as a stack. So a last in, first out type of memory is a register stack, and so multiple registers can be organized into a stack. And the way the stack works is that data is stored and then retrieved in reverse order. So the stack will have the top of a stack, which is one register which will be on top, and then there will be towards the bottom of the stack that will be your nth register, depending on how big the stack is. So when the data is stored into the stack, first of all, it sits on the top, and then when new data comes into the stack, the new data pushes the data that's on top to the second register towards the bottom. So the data will keep on being pushed into the stack, and as it's being pushed into the stack, it sinks lower and lower into the stack, into the bottom of the stack. When data needs to be retrieved out of the stack, what's going to be read is just on the top of the stack, which is the last data to come in, and that will be read out. And as it's been read out, the data below it will come up on top of the stack, and so on and so forth. And sometimes, in fact, many of the times, part of RAM is used as stack by the processor. And in the case where RAM is used as a stack, data is not pushed down to the top of the stack, but the top of the stack moves. So the top of the stack is tracked by a special type of register, which is called a stack pointer. And the stack pointer tracks this by containing the address to show where the top of the stack is currently. So take, for example, in this picture, whereby data is, this RAM module is being used as a stack. What will happen is that the stack pointer, which is a special register, it will contain the address of this particular top of the stack, which is the stack itself. Now, when data is popped into the stack, is pushed into the stack, that is when you want to store data, you will store the data. In this case, it has only a single length of data in the stack, which is at FFEE. Now, as more data is being pushed into the stack pointer simply changes by tracking now that the top of the stack will be pointing to the latest data that was pushed into the stack. So adding data into the stack, we are simply saying we are pushing it. We use the word push to add more data into the stack. When data has been retrieved out of the stack pointer now starts to decrement. It decreases now. It will move to the next point, and that piece of data will consider to have been popped out of the stack or retrieved. And so in this case, the data that was put finally into the stack, which was the last to come in, will have been read out, will be the first one to be read out, because the stack pointer will point to it always. The last type of special kind of memory that we'll look at is what's called chart coupled device, or the CDD type of memory. In this case, data is stored as charges within capacitors, Unlike DRAM, this type of memory does not have transistors, so there are no transistors in this type of memory. And it's very good in storing optical images and converting them to electrical signals. So it's used for high density memory. So the CDD memory consists of channels of long rows of capacitors, such as the one shown here. The way the data is being stored is that the charge moves serially from one capacitor to the next, and the capacitors need to be refreshed periodically, much like the DRAM. Having looked at flash memory, memory expansion, and special types of memory, we are done with part 3 of this lecture series. Please do refer to your reference text to look at examples of problems for practice, so that you cement the concepts